Water. You see it every day, right? It seems so simple, so normal. But let me tell you, this everyday molecule is a total chemical rule breaker, just full of surprises. So let's dive in and uncover the secret power that's hiding in every single drop.
And we can kick things off with one of its biggest mysteries. I mean, really think about this for a second. You drop an ice cube in your drink, it floats. No big deal. But for pretty much every other substance on this planet, the solid form is denser and sinks right to the bottom of its own liquid. So what makes water so special? What makes it the ultimate exception to the rule? Well, we're about to find out. The answer to why ice floats and to a lot of water's other weird abilities isn't something you can see on the surface. Nope, we've got to go deeper, way down to the molecular level, to really get what's going on with these slightly sticky molecules. To get this whole stickiness thing, we need to wrap our heads around one key concept: electronegativity. It sounds super technical, but it's basically just a measure of how much an atom hogs the electrons in a chemical bond. And when it comes to water, let's just say the oxygen atom is the biggest electron hog you'll ever meet.
So here's how that all plays out in a water molecule, H2O. You've got the oxygen and two hydrogens sharing electrons. That's called a covalent bond, and it's really strong. But because oxygen is such an electron hog, it pulls those shared electrons a little closer to its side. This whole situation gives the oxygen end a slight negative charge and leaves the two hydrogen ends with a slight positive charge. And just like that, our molecule now has two poles, kind of like a teeny tiny magnet. It's become polar.
And we all know the fundamental rule that comes next, right? When you're talking about charges, opposites attract. This super simple fact is the key to, well, pretty much everything that follows.
Okay, so this polarity means the slightly positive hydrogen of one water molecule gets attracted to the slightly negative oxygen of a different neighboring water molecule. That attraction? We call that a hydrogen bond. And here is the absolutely crucial difference. The strong covalent bonds are like the superglue holding the atoms inside a single water molecule together. These hydrogen bonds, on the other hand, are much weaker, like little magnets linking separate water molecules to each other.
Now, you might be thinking, a weak bond, so what? Well, a single hydrogen bond is weak, but when you get trillions and trillions of them all working together, that's when you start to see some truly incredible, almost miraculous effects that literally make life on Earth possible. Let's check them out.
First up is something called cohesion. That's just a fancy word for water molecules sticking to each other. All that sticking creates a kind of skin on the surface, which we call surface tension. It's strong enough that insects like the water strider can literally walk on water. And it's the same force that helps plants pull water all the way up from their roots to their highest leaves, totally defying gravity.
And this stickiness shows up in some really surprising everyday places. For instance, have you ever really wondered how a hair straightener actually works? Well, the secret is all about playing around with these very same hydrogen bonds. So your hair's natural shape, whether it's curly or wavy, is held in place partly by hydrogen bonds in its proteins. When you apply a ton of heat, say between 150 and 300 degrees Celsius, you're actually breaking those bonds. Then, as you pull the hair flat and it cools down, new hydrogen bonds form, locking it into that new straight shape. Of course, we all know it's only temporary. The minute your hair gets wet, those hydrogen bonds just snap right back to their original happy place.
Okay, so beyond just being sticky, those hydrogen bonds give water another superpower, an incredible ability to resist changes in temperature. It acts like a great stabilizer for our entire planet and even for our own bodies. Just look at this to see how wild this is. Compare water to a similar molecule, hydrogen sulfide. Without any hydrogen bonds, it boils at negative 60 degrees Celsius. It's a gas at room temperature. Water, on the other hand, boils at a sizzling 100 degrees. That massive difference is all the extra energy it takes to break apart those sticky hydrogen bonds and let the molecules finally escape as steam. And why does this matter so much? Well, it means our oceans and lakes don't just boil away in the summer or freeze solid in the winter. They create stable homes for life. It's also why our bodies, which are mostly water, can maintain a nice, steady internal temperature. And it's why sweating is such a brilliant cool-down system. When that sweat evaporates, it takes a huge amount of heat energy with it. So all of this, the stickiness, the temperature control, it all brings us right back to where we started, back to our original mystery. How did these simple little hydrogen bonds solve the puzzle of floating ice? Okay, so to really appreciate how strange water is, you have to remember the normal rule. For pretty much everything else out there, when you freeze it, the molecules pack in tighter. The solid becomes denser than the liquid. And it sinks. That's just normal physics.
But water? Well, once again, water just loves to break the rules.
And here is the big reveal. In liquid water, the molecules are like a jumbled mess, tumbling around each other, with hydrogen bonds constantly breaking and reforming. But as water gets cold and starts to freeze, those hydrogen bonds lock the molecules into place. They form a really organized, open crystal structure. And get this structure actually holds the molecules further apart than they were in the liquid. The result? Ice is about 9% less dense than water, and that is why it floats. And this isn't just some neat party trick in your drink. It's absolutely essential for life on Earth. That layer of floating ice acts as a perfect blanket, an insulator, protecting the liquid water underneath from freezing solid. This is what allows fish and all sorts of other aquatic life to survive through the winter. The source text for this explanation highlights these properties as essential for life.
So when you boil it all down, it's this beautiful paradox, isn't it? These seemingly weak little attractions between water molecules are exactly what gives water its world-changing, life-sustaining strength.
It really makes you wonder, doesn't it? What other things in our world look small or weak on their own, but become unbelievably powerful when they all work together? Something to think about.